Okay, on to problem number 2 here. And we're going to need some of the stuff from the notes, so I've got that up on the side screen there so that you can see how I'm sort of referencing things as we go through these problems. So the first question we have is perform the operations in the assembly code, use the initial register values after each instruction executes, show any changes to registers, and show any updates to the NZCV bits at the right of the instruction. And so we have the register values listed, and that's what's in the registers as well. So let's go ahead, and the first thing we're going to do is an add S, and we're going to add 5555555 plus AB. So I'm going to go ahead and just work that out in full binary to make sure that we can do the easy way for the NZCV bits. You could also run this in Kyle or do the hex math and then see what happens based on that. But I think probably for sort of to be prudent, we can just do the math. So 55555555 is just a bunch of 0101s repeated. And we may be able to see the pattern once we've done this for a few. So 1010 for A. So this is 5555 plus AAAB. And then for B, 1011. So we're adding those together. 1 plus 1 is 0, carry the 1. 0, carry the 1. 0, carry the 1. And you can start to see the pattern, right? That we've got alternating zeros and ones there. And we're going to keep carrying because we've got a carry already. And so we're actually just going to finish this off and realize that we're going to have zeros the whole way across. And I don't know that we even need to write it out. We know that this is 0, carry the 1, 0, carry the 1, 0, carry the 1, 0, carry the 1, right? So we carried a 1 out the left side, which means our C bit is easy. That's going to be 1, right? We did carry, and so we know that that's going to be the C bit. Our result from this instruction, where we did an add of R0 plus R1 goes into R3. So our result of zeros is going to go into R3. And we're going to update those bits because there is an S on that instruction, so it sets the status bits. We are going to set the N bit based on this result, which is all zeros. That is not a negative number. We're setting the N bit to be the same thing as the leftmost bit in the answer, and that leftmost bit is a 0, so the N bit is also going to be a 0. The Z bit is set Z equals 1 if the entire result is 0. Z equals 0 if it's anything but 0. So Z is equal to 1 here because we do have all zeros. We already know the C bit because we found that from having a carry out. We could also look at our rules in the notes here for when a carry out happens, and that's in the arithmetic instructions. That if we scroll down and we see the rules for the C bit for unsigned addition, so this is this set of rules right here. And remembering that X is really large, that condition, we consider something to be really large if it has the leftmost bit set. So here we have X is not really large because R0 does not have the leftmost bit set. Y is really large. And then the result is not really large. So R, the result, is not really large. If we look at our rules, X is really large and Y is really large. That's not true because X is not really large. X is really large. Again, not true because X is not really large. But here, Y is really large. It is because its leftmost bit is a 1. And R is not really large. It is not because its leftmost bit is a 0. It is just 0. And so we can see that this third rule is actually correct. This is true. And so C equals 1, we should have a carry out. We can verify with this rule. Now let's check our rules for signed addition. Keep in mind, doesn't matter if this is signed or unsigned. We're still going to apply the C and B bits. And here we can see our rules for signed addition. We would have a V equals 1 if we have a positive plus a positive equals a negative, or a negative plus a negative equals a positive. Keep in mind, we do treat 0 as a positive here. So again, looking at the leftmost bits, for X we have a positive. For Y we have a negative because its leftmost bit is a 1. And we have a positive for our result. Positive plus a negative equals a positive. That's not one of our cases, so V equals 0. Okay, so that's it for the first one. Next up, we've got add into R4. R2, R2, LSL2. So this is the addition with a barrel shifter. And that's in the end of the notes here, so instructions with the barrel shifter. And what's happening here is that we are shifting the second operand before it goes into the ALU. So before we do the add, we're going to shift the second operand by 2 as it goes in. So we're taking the value in R2, we're shifting it by 2, but just sort of temporarily as it goes into the adder there. And then we're adding that to the original value in R2. So again, this does not actually change the value in R2 here. We're just actually going to do it sort of temporarily. So R2 starts as 0, 0, 0, 1. I'm just going to look at the rightmost bits here because we're not going to need to see that. We're adding that to that value shifted by 2. So we're going to just shift this over by 2, means the 1's going to be there. And LSL does not do anything to the right side. We just shift in zeros on the right. And so that 1 moves over, and we end up with 0101, which is OX5. And so our value that goes into R4 is OX00000005. Because there's no S on the end of this instruction, we do not update the NZCV bits, and so they would stay the same as they were before 0110. Right, so that's just same as previous instruction. And you can notate that to make sure I know that you know what you're doing, if you would like. The next instruction is an ASRS, R5, R1, 8. So we want to look at the logical instructions here and look for the ASRS instruction. You're also more than welcome to make a more condensed guide for yourself, but hopefully you can just find these in the instruction manual. So we see ASRS R5, R1, 8. That should match one of these instructions. And it does match this one, other than not having the S on the end, but keep in mind that's sort of a standard thing. The S is just we're setting the status bits. So ASR, we have our destination register is R5, our source register is R1, so we're shifting what's in R1 right now, that AAAB, and we're shifting it by an immediate of 8. So we're shifting right by 8 bits, and that's equivalent to 2 hex digits that we're going to shift right by. But we can do the bits here as well. We want to then look at the guide here and see that ASR is shifting to the right. It's shifting out the rightmost bit into the C bit, and we are shifting and copying the topmost bit. So this is arithmetic shift. It is keeping the sign of the number the same. So if we have a 1 in the leftmost bit when we start, we're going to have a bunch of 1s at the left whenever we're done shifting. And so that's what we're going to have here. So we'll start with this 1010, 1010, 1010, so on and so forth. That's the AAAA. 1, 2, 3, 4, 1, 2, 3, B. All right, so that's that value in binary. And each shift, we're going to copy the leftmost bit, and we're going to shift everything to the right. So we're going to have a 1, and then 1010, 1010, 1010. And then the rest of the bits would stay the same, except now we've shifted off. The end of that would have ended in B, 1011. Now we end up with 0101. And that 1 goes into the carry bit because that's what we shifted off last. So we'll continue this process, and really we can just think about this in terms of the hex for simplicity, and know that really we're shifting 8 bits, which is going to be 2 hex digits. Each hex digit is 4 bits. And so we know that our final answer is going to be FF, and these two get shifted off of the end, that AB, that gets shifted off of the right end, and the last thing to get shifted off is going to be the top of that AB. So the 1010, 1011 gets shifted off. The last bit to get shifted off is going to be our C bit here. And so we've got FF and then a bunch of A's, because we shifted off the B to the right. That's what's going to go into R5. So FF and then A's. We are setting the status bits because that ASR ends in an S. And so we've got R5. The value of R5 is going to inform our status bits. Because the leftmost bit is a 1, F has a 1 at the leftmost bit. N is a 1. Z is a 0 because this is not just 0. The only case we have that we would do that is what's in R3, which is all zeros. The C bit is a 1 because that's what we shifted off last. And V stays the same. V doesn't actually mean anything for an arithmetic shift because it's not an addition or subtraction. And so we don't actually change the V bit here. It just stays the same. Last instruction here is a UBFX going into R6 of R1, and then 5 and 8 are the immediates. So again, we need to look up this instruction, find where UBFX is in our instruction manual, and that's right here. So UBFX is the instruction we're looking for. We recognize that R6 is the destination register, RD. RN is the source register, R1. And then the least significant bit, the LSB, is 5. And the width is 8. And so we'll be able to read the instruction format to understand what's happening here. So let's copy that value and write it out in binary here, at least for the bits that are going to be necessary. And again, we're taking from R1. So we're going to have that 1010, 1010, 1010, 1010, 1010, so on and so forth. Okay. And we can number our bits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I think that's going to be enough for what we need here. And we want to sort of write out what this instruction says to do. So RD here, and just following from the manual, from what our guide says. So RD at width minus 1. Width in this instruction is the 8. So we're again just referring to the parameters that are there. So width is 8. So RD at 8 minus 1, which is 7, down to 0, is getting the value. So it's taking its value from Rn, and that's from LSB, which is 5, up to width plus LSB minus 1. So 5 plus 8, 13 minus 1 is bit 12. So what UBFX is doing is it's taking something from this value that we've written out and written out the bit numbers for, and it's going to put that value into R6 at the lower bits, so the 8 bits at the rightmost part of that register. So we're just going to take, starting at bit 5, that's right here, bit 5, count 8 bits, 1, 2, 3, 4, 5, 6, 7, 8. That's over to bit 12, which is what we expect, right? That's what we wrote here, 5 up to 12 inclusive. And then we're going to put that into register 6. We need to have that as hex instead of as binary. So 0101 is 5, 0101 is 5, and so our result's going to be OX 00000055. NZC bits are not updated by this instruction, right? UBFX does not have an S attached to it, and so we are not going to update the status bits. And so that is it for problem number 2.